hopefully. And so I've been tasked today with doing a short wrap-up session. This will take less than 10 minutes, and then we can have a few questions if anyone wants to type into the Q&A or the chat or what. I guess the Q&A would be the best place. And then I'm going to do a section on solving Markov decision processes, and that'll take about an hour plus, and we'll have time for some questions. I'll do some demos and so forth, and that'll take us up to the break. So that's, unless I'm mistaken, I think that's the schedule. So yesterday we talked about Markov decision problems or processes. Unfortunately, I don't have Mike's cool tablet pen thing, so I guess I'm the Luddite of the group and a little old-fashioned. So I haven't got that technology yet, but you'll just have to bear with me saying things rather than writing them on these slides. So we have MDPs. They're characterized by a set of things that we have to define. We have a set of state variables S, of control variables A. There's some kind of reward or objective function that defines what it is that we're trying to maximize. And that's going to be a function of S and A and possibly of some random noise E. We have a discount factor, which is related to the discount rate by 1 over 1 plus R, where R is the discount rate. And this is the discount factor is basically measuring what the utility of the reward next period would be for us in relative to 1 now. So typically that's less than 1. So we prefer things immediately to things in the future. We can certainly talk about how that relates to things like sustainability. A lot of people, particularly non-economists, don't seem to like that. Economists seem to like discount rates. But we're really not going to get into that as a lengthy discussion. That would be a good thing for virtual beers. And the final thing that final part of the definition of a Markov decision process is some kind of transition rule or transition probability. And this is typically the hardest thing to define. We are going to either use a transition probability matrix, which I'll call P, which is the probability that next period's state, S plus, conditioned on this period's states and actions. So that would be one way to define that transition law. Another way would be to use a transition function where we're actually defining S plus as some function of current states, actions, and a random noise term. By the way, sometimes economists use the word shock for E. So when if I slip into that that way of talking, that's just the same thing. A shock and a random noise variable are the same thing. Shock is used a lot in economics, but isn't used as much in biology and other fields. It's used a lot in engineering too. Our goal in this whole process is to find a strategy. And I've used the script A of S to really point out that the strategy is a function of S, of the states. It's a mapping of the states to the actions. And it's telling us what we should do given each state. So the states are going to change according to this transition rule that we've got from the matrix or the function. And so each period will potentially be in a different state, and we would have a different action to take. So this is a state-dependent strategy that we're trying to find. And basically what we're trying to do is maximize our discounted sum of expected rewards. And you can see that written out there. We're maximizing over this strategy, this expectation of this reward function that we've got. And I've written it in terms of E. But remember that S, future values of S are also functions of E. We can also talk about a diagrammatic view of an MDP. This is often a good way to sort of visualize what's going on. In the top right, I've got a very simple thing where we have states and actions on the left-hand side. Both of those go into a utility or reward function, and they both also go into the future state value, the S plus. So that's a very simple one. We can add in more details by adding in noise terms like E. So you see E is an intermediate variable, if you will, but it has no arrows going into it. I, on the other hand, is an intermediate variable where it's a function of S and A. So the arrows are denoting functional relationships. And we sometimes call these parents and children. So, for instance, S is the parent of I, A is a parent of I, and so forth. And on the lower right hand side, I've got a much more complicated example. I have multiple states, multiple actions. In this case, I'm also showing two variables that are kind of intermediate variables called P1 and P2. Those I think of as performance indicators. So we have certain variables that we think of as things that we're interested in either maximizing or minimizing, and they're going to go in and be they're going to go into our utility function and have some kind of trade-offs expressed in the utility function. Last night we didn't get a chance because we ran out of time to talk about the Markov property. Basically, the Markov property it's a very important property for us, and basically, in a nutshell, it's saying that stuff in the past, so all these state variables which I'm highlighting, I hope you can see my highlights. Yes, no, maybe? I don't have a visual on anybody but Suzanne, and she's not paying much attention, I guess.
Yeah, no, we can see it. No problem.
See it. Okay, good.
Yeah.
All right. So the history of stuff, ST minus 1 to S down to S0, doesn't actually figure into this function. So we can ignore all of that history. All we need to understand what's going to happen in the future is the current state and the current action. Okay, so that's the Markov property. And Michael had an exercise that I've redone here because we didn't get to it. And basically, it's something where a problem where you have to take a function that involves both current S and past S and convert that to a Markov process that involves just current S. And so you might think about and try to ask yourself how you could recover the Markov property in that situation. I also want to just point out that when we get the solutions, if you will, to Markov decision processes, we're trying to get this strategy, this decision rule. I'm using those two terms interchangeably, a strategy or a decision rule, and we want to find the optimal possible strategy, the one that gets us the best rewards, and we'll also get the so-called value function. If you recall from this slide, down at the bottom, I've defined this value function as a function of the states. It's that stream of expected discounted rewards, and so we will get that as a freebie, if you will, and that'll enable us to talk about how valuable it is to be in certain states versus other states, and we'll also get into issues of that Mike touched on yesterday about the value of information when we get into adaptive management problems and so forth. Now, David also talked yesterday about certain types of uncertainty that we face, and I want to emphasize this. I believe David had this sort of a way of discussing different types of uncertainty. There's environmental uncertainty, which is that we don't know what the future holds, and that's sort of inherent to the system. We can't get rid of it. We can't reduce it. It just is part of the system. That we have stochasticity in the behavior of the variables that we're interested in. Uncertainty and controllability is that we don't know what our actions will do. This is really a kind of environmental uncertainty, but it's specific to the whole controllability of the process. Now, structural uncertainty is that we don't know how things work. And we also have observational uncertainty in that we don't know what's happening now. And so both the environmental and controllability uncertainty we can handle in our traditional MDP framework. But the other two types, we really need an expanded framework in which to work. And that's the adaptive management that we're talking about in this workshop is primarily concerned with structural uncertainty. The basic tool used to address observational uncertainty is a so-called POMDP, which stands for partially observable MDP. And Iadine is going to talk about that a bit on the last day of the workshop. That's basically what I have for wrap-up. So if there are questions, this would be a good time to ask them. And once we get through with that, I'll move to the slides for the main lecture today, or at least before the break. And then Iadine is going to take over after the breakout sessions and talk a bit about Bayesian updating and Bayesian statistics, which will then lead into our discussion tomorrow specifically about adaptive management. So are there questions, concerns, chats? I see the chat room. Anybody been monitoring that wants
Yes,
to
I am
speak up?
monitoring, but I don't see any messages yet. No questions yet.
Okay.
Okay.
Well, I thought that was very clear, everything you said.
Okay, good.
Yeah. The reason
Easy for you to say,
delay
Iadine.
is that we're muted. So when you ask us something, we got to click to get on it.
Okay. Well, if there are no, I see a question in the Q&A. It says, out of curiosity, is there a case study where future rewards would be more valuable? I'm not quite sure what you mean by that. It's certainly possible that we have current rewards which are negative even, but future rewards are positive. For instance, if we were going to build something, we'd have the immediate cost of building it, but the rewards might be generated over the future. Something that
maybe he's thinking about
periods.
Maybe he's thinking about the discounting. How the discounting usually, you have that weight, and it goes, it goes monotone usually. The discounting, right, as you go.
I think if I can cut in, I think in economic studies, the sense in which rewards might be worth more in the future is usually modeled outside of the discount factor. I've seen studies with so-called hyperbolic discounting where the discount factor may change over time. That's been applied in climate change policy research, but I personally haven't seen one where it gets larger than one, because again, other sources that may increase the value of rewards. I guess a really simple example that might be handled with a state variable is prices. Prices in the future may rise, but I haven't seen a discount factor bigger than one.
I do think people are starting to do unusual things in finance because they're doing things where it's not time inconsistency and stuff like that. So
yeah,
I have an application.
Okay.
I have an application. I have a case study where, for conservation of biodiversity, we know that as species get more threatened, the amount of funding increases over time. So in a way, the reward you would receive from saving a species, the amount of money you will get will be more important. But the amount of things you can do for that species, because they're low in numbers, would decrease. So it's a very interesting problem where I would say it's potentially a non-stationary Markov decision process. So yeah, as David said, you would probably need to account for time and as also a state variable. Does that make
Yeah,
sense?
and I could just think of a simple example where you say, if you know that the world is going to get really bad next period, then you may be willing to give up more utility this period in order to ensure that you get some next period. And in that case, you could have a discount rate that's above 1, or a discount factor above 1. Normally, though, I would say this is not the normal situation. So most of the projects that we would be talking about would not have that sort of feature. Hopefully that answers that question. And if that's the case, I am going to move on